Hello. In this video I want to discuss the complex exponential. So the question is, if we are given a complex number z, say a plus bi, how should we define e to the power z? The right definition turns out to be the following, right? So it's e to the a times cos b plus I sine b, right? So the real part a goes in there, and the imaginary part goes in there. Right, so note here what we've got, e to the a, that's just a normal real exponential. Now, let's see. As an example, e to the 2 plus I, right, so the real part is 2, so that would be e to the 2 cos imaginary part 1 plus I sine imaginary part, which is 1. Now you may very well ask yourself, and you're completely justified in doing that, why on earth would we take this definition? What does the trigonometric functions cosine and sine have to do with an exponential function? Well, it turns out that they're actually intimately related. And as a good motivation for our definition, we can look at Taylor polynomials. So for the function, the real functions, e to the x, cos x, and sine x, the Taylor polynomials about 0 are excellent approximations for the functions. Right? So we can say, well, e to the x is approximately 1 plus x plus a half x squared plus 1 over 6x cubed plus 1 over 24x to the fourth plus 1 over 120x to the fifth plus 1 over 720x to the sixth, and so on. Right? So we've gotten up to the sixth term for a Taylor polynomial. Likewise, we can write down the Taylor polynomial for cos x and say cos x is approximately 1 minus a half x squared plus 1 over 24x to the fourth minus 1 over 720x to the sixth, and so on. Right? And sine x would be approximately x minus 1 over 6x cubed plus 1 over 120x to the fifth, and so on. So now we can ask ourselves, if we take a real number b, how should we define, what should e to the ib look like? Well, we'll note that here in the Taylor polynomial approximation for e to the x, this makes sense even if we plug in a complex number, right? So in particular, we're just taking x to integer power. So if we replace x, the real x here, with a complex number, this expression still makes sense, right? So it's a good guess to say, well, if we plug IB in there, that should give us e to the IB. Turns out that this is exactly what you have to do. We can't make it rigorous at this point because we don't have the sufficiently sophisticated mathematics at our disposal, but if you persist, then in your third year you'll get to see how this is done rigorously. Right. So now let's see, just as a motivation, if we plug IB into x in the Taylor polynomial for e to the x, we get, well, e to the IB should be approximately 1 plus IB plus a half IB squared plus 1 over 6 IB cubed plus 1 over 24 IB to the fourth plus 1 over 120 IB to the fifth plus 1 over 720 IB to the sixth. Right. And we just multiply out the powers. So we're going to get 1 plus IB minus a half B squared minus 1 over 6 B cubed I plus 1 over 24 B to the fourth plus 1 over 120 B to the fifth I minus 1 over 720 B to the sixth. Right? Now let's group together all the real and all the imaginary bits. Right? So we group together all the real bits. So we're going to have a 1 minus a half b squared plus 1 over 24 b to the fourth minus 1 over 720 b to the sixth. And if we throw in, now look at the imaginary parts, we throw them all together. Right, so we go and we look for all the terms here with an I in it. So we get b minus 1 over 6 b cubed plus 1 over 120 b to the fifth. And then an I. So now if we go back and we look at the Taylor polynomials for cos and sine, we'll see in here if we make x equals b, then we get exactly the real bit here. And in here for sine, if we make x equals b, what are we going to get? Well, we'll get exactly that. So then we can say, well, this is approximately cos b plus sine b I. So we take that as our definition, motivated by these Taylor polynomial arguments. We say cos to the ib, e to the ib is cos b plus sine b I. Right? And then we would expect our complex exponential to behave similarly to the real exponential. So in particular, we should have e to the a plus ib to be e to the a times e to the ib, which is then e to the a cos b plus sine bi. Right. So that's just a little motivation for why we define complex exponentials in this way. Now, an important special case is if we write z in polar form. Right? So if we write z in polar form, so z is r cos theta plus I sine theta, then what is e to the then we can write z in this form. Right? Z would be r e to the I theta. Right? Because remember, per definition, r e to the I theta is r cos theta plus I sine theta, which is z. Right. So that means that what we've got here is a very nice and convenient notation for polar form. Okay, so for example, let's write the complex number z is minus root 3 plus I in the polar form r e to the I theta. Well, so our r is mod z, which is 2, and now we need to find our theta, and let's just take our principal argument. Let's take our theta between minus pi and pi, right? So we want this theta so that cos theta is real part over modulus, and sine theta is imaginary part over modulus. Right. So now we need to solve these two equations, right, and find the common solution. So cos theta is minus root 3 over 2. It tells us either theta is 5 pi over 6 or theta is minus 5 pi over 6, and sine theta as a half tells us either theta is pi over 6, or theta is 5 pi over 6. Right? So we need a value of theta that satisfies both of these equations. So we look for the common one. Theta is 5 pi over 6. So what is z? Z is r, which is 2e to the theta I. So e to the 5 pi over 6i. And there we go. Now, just note that if we use this very convenient notation for the polar form, then the Moore's theorem, which tells us how to take integer powers of complex numbers, reads in the following form. So r e to the theta I to the power n is r to the n e to the n theta I. Right, for a non-zero integer n. So for instance, if we take z, the complex number root minus root 3 plus I, which in the previous example we showed was 2e to the 5 pi over 6i, then z to the 10, what will that be? It's going to be 2 to the 10 e to the 50 pi over 6i, so 2 to the 10 e to the 25 pi over 3i, and that's 2 to the 10 e to the 8 pi plus pi over 3i, and that's equal to 2 to the 10 e to the pi over 3i. Right? This last step here, it's just because of the periodicity of sine and cosine. So if we add an integer, an even integer multiple of pi to the argument, it doesn't change the complex number. Right. That's the complex exponential.